Another well-known window is the so-called Kaiser window. It's given by these more complex equations here, where the Bessel function is used. We have here this IOs, the Bessel function, given by this function here, where in practical designs often the first 20 terms are used, and you can refer for these wavelets and filter banks by Strang and Nguyen. And the parameter beta here is used to trade off the transition bandwidth of the filter and the stop band attenuation. So an example for L equals to 16 and beta equals to 2, we have here, there is a numpy already embedded Kaiser function, so we don't need to write all these equations, so it's very convenient. We can use a numpy Kaiser. Here we pass the length and the beta, and here we have our plot of the Kaiser window, and with frec we obtain the frequency response. And here we can see that the main lobe, so the pass band and the transition band for beta equals to 2, is even narrower than for the sine window. The first lobe also has about minus 20 dB attenuation, but the further side lobes don't have much increasing attenuation. If we increase beta from 2 to 8, so we just change this value here, and we have this shape for the Kaiser. And now we have a very different frequency response when compared to this one. So here we can see the other extreme with a very wide main lobe, so the pass and the transition band, but the first side lobe we already have about minus 60 dB attenuation, which would fulfill our requirements, for example, for an anti-aliasing filter.